And it is my pleasure to introduce tonight's speaker, Dr. Xinnan Du, who's also joined us mute there. Xinnan is the Outreach and Engagement Manager at the Kavli Institute for Particle Astrophysics and Cosmology, or KIPAC, at Stanford University. She got her PhD in astronomy in 2018 from UCLA, and her research focuses on the physical properties of the interstellar and circumgalactic gas in distant star-forming galaxies. Before moving to Northern California, Xinnan spent 3 years at UC Riverside as a postdoctoral scholar, outreach director, and program manager. She's very enthusiastic about public outreach with a long-term career goal in informal science education. Xinnan hopes to inspire and engage everyone in learning astronomy through various outreach programs. So I think we're going to get a taste of that in tonight's presentation. So please join me in giving her a warm welcome. And Xinnan, the Zoom floor is yours.
Well, thank you very much for the nice introduction, Marianne. Let me start sharing my screen. Okay, I guess that looks fine.
Looks good.
Awesome. Well, hello, everyone. My name is Xinnan Du, and as Marianne said, I am currently working at KIPAC, and I am actually very new to this role. This is my fourth or possibly fifth, starting off my 5th month into this role. And I was very honored to have been connected with SMCAS during one of my first days here in the Bay Area. So as a disclaimer, tonight's talk is going to be on astrobiology, and this is actually not in my specialty area. But I found it very fascinating, given it's an interdisciplinary field. And, it actually requires experts from multiple STEM fields to work together to figure out answers. So I hope after this talk, you're also going to, at least be enlightened by some of the, I'm not sure, I will be giving answers to a lot of key questions, but at least, to introduce some of the frontier and key questions that we're having in mind. So to start with, I actually wanted to ask if anyone recognized this painting. If you know its artist or its theme, what it's called, anything.
Is that Paul Gauguin?
Yes.
But I don't know the title. Wow,
this is, I didn't know about this painting until I searched up this title. But it's a quite long one. It is, where do we come from? What are we? And where are we going? So this is sort of summarizes the key questions, not only in astronomy, but also specifically for the field of astrobiology. So by studying the origin and formation of the universe, how our galaxies and stars and it's essentially life, how they evolved into this state, we're asking the question about our past. Right, and we're still trying to figure out an answer or a clear definition of life and intelligence to figure out who we are, essentially. And also about our future, it has a lot of things to do with the evolution of life on Earth, our surrounding environment, and where the universe is going. So I'm hoping that these 3 questions are going to be at least somewhat answered by my talk today. So to start with, I actually wanted everyone to think about if you were the one in charge of making a definition of life, what would you say? What properties would you say that life typically has? And here, of course, is an example of a living animal on Earth. And based on this, any ideas how you would define life? Feel free to put it in the chat or directly unmute yourself. And don't worry, I mean, we don't even have an agreement of what life is. So this is all just whatever you think that is important. Yes, reproduction. And when you think about, yes, made of cells, adaptation to the environment, right? Any other properties? Yes, consumes energy. Yes, growth and wow. I'm very surprised. Yes, growth and development, responding to different stimuli. I feel like okay. Yes, this is basically what I'll be talking about the next couple of slides. So it sounds like people already have a pretty good idea. And if I were to define it, right, and looking at a cat, I might say, okay, well, it consumes energy, it can move, and it also releases heat. But the same properties would also describe a car. So that is not necessarily, you know, a definite definition for life. And then I might also add, okay, well, it's made up by cells, right? But for these real wood furniture, they're also made up by cells, but they're not a living organism. Or I could also say it can grow. Well, a balloon can also grow in size, but it's not life. So there are very fine lines and you know, different criteria that we may use. And it seems like it's very complicated to actually give some definitions of life. So many of these general properties that we find very common for life on Earth have already been mentioned in the live chat. So out of these, I would actually like to highlight two things. So reproduction and evolutionary adaptation. So reproduction, it means life, it can produce or is a product of reproduction, right? It can take various form, either sexual or asexual. And both evolution and responding to the environment, it actually helps the entire species to survive, that they gradually evolve to better suit to the environment. So these are, again, some of the common properties of life on Earth, but there are always exceptions. For example, when we're talking about virus, we're talking about prions, there are always things that doesn't fit into these categories. But these are, in general, pretty good guidelines. So when we're looking at the composition of life on Earth, we would find that all life on Earth is carbon-based. So here is actually a pie chart that shows the chemical composition of human body by weight. You can see that most of the mass actually goes to oxygen. So why do we not say that life is oxygen-based? Well, that is because most of the oxygen is actually in the form of water, and that is not an organic molecule. And specifically for carbon, even though it is not the most abundant element in the human body, it is essential for cell structure and function. So why carbon? Why not all the other elements in the periodic table, right? So one thing that is pretty unique about carbon is that it can bond up to 4 atoms at a time. And not only that, it can also form both single and double bonds. So that would actually give carbon to have a lot of variety when forming patterns, right? There could be chains, could be rings, or it could also be branches. So that allows a huge variety, not only in these skeletons, but also in its function and eventually life forms. So, well, if we say it can bond 4 atoms at a time, well, silicon can also bond 4 atoms at a time. So is silicon-based life possible, do you think? And again, feel free to directly type in the chat. We already have some disagreement based on the first two answers. And again, only in Marvel Comics. Yeah, there's a good point. Silicon might be possible, but carbon is more common. Yes. So you may find that a lot of, during my talk, I would ask or use the word possible a lot. So possible doesn't mean it's probable or it's likely, right? It's whether it's at all. So, based on chemistry, it's not impossible. And silicon can also bond 4 atoms at once. But there are some drawbacks when comparing to carbon. So first of all, well, because the silicon atoms, they're bigger, so the bonds are weaker just because the electrostatic force between the nucleus and electrons, that is weaker, right? So whatever molecules it forms, it is fragile. It's more fragile than what carbon would form. And typically, silicon would only form single bonds. So that actually significantly cuts the great variety, both chemically and also structure-wise, and how it evolves in chemical reactions. And finally, carbon dioxide is gaseous, but silicon dioxide is solid, and that's what we mostly find in rocks, right? So it can not move a lot, and in fact, carbon dioxide, the cycle of carbon dioxide is very important for regulating the climate on Earth. So we find carbon dioxide in the atmosphere. It can dissolve in water to form carbonic acid, and it can also react with rocks. So there is a whole cycle that would recycle carbon, but for silicon, it's not that possible. So now we've looked at some of the chemical bases of life. And now I wanted to also make another clarification of when we're talking about searching for extraterrestrial life, are we searching for intelligent life, or are we searching for very basic life forms? And we're actually searching for both. So there are different probes for different kind of life forms, and I will mainly focus on searching for basic life for this talk, but also a little bit of SETI related materials at the very end of this talk. But just keep in mind that we're not always communicating with intelligent life, and therefore there are always different kinds of signals, sometimes confusing, that we receive that we would have to interpret, hopefully the correct way. So before talking about where to look for extraterrestrial life, we might want to take a closer look at what life actually needs. I can hear my own echo. So there are 3 things that we sort of at least need to consider. One is the building blocks of life, which is matter. Second is energy, because nothing can basically function without energy input, because we need to metabolize and keep ourselves alive. And third is liquid media, which will help transport chemicals and also facilitate chemical reactions. So when we're looking at building blocks, as we saw in the pie chart before, there were 4 elements: oxygen, carbon, hydrogen, and nitrogen, that forms 86% of living organisms by mass. So basically, we will try to at least need to look at places where these elements are abundant. But it turns out that building blocks should be pretty widespread in the solar system and also in other stellar planetary systems. These elements, we can find them on Earth either in the atmosphere or oceans or both, and they could actually have been brought by comets or asteroids during the early times of Earth history. So the building block aspect, it's actually not a constraining factor, at least at this point to our understanding. And in terms of energy, there are also different energy sources that we could possibly use. Most of the living organisms on Earth relies on solar radiation, right? But as you go farther and farther away from the sun, the energy gets weaker and weaker. There is also chemical energy, especially in the bottom of the ocean and near the deep sea volcanic vents, where microbes could use to metabolize. And finally, there is the internal energy that planets or moons get during their formation through various forms. So accretion, that's when they were gaining mass at early times. There's differentiation, basically the heavier or denser materials sink to the bottom, and the lighter elements float to the top. And that's also how the Earth has a metallic core, and also the relatively less dense rock form the crust and also mantle. Finally, there is radioactive decay, and that is from heavy nuclei to form lighter nuclei. Radioactive decay actually accounts for more than 50% of the internal energy here on Earth. And typically we would see, decay of uranium, potassium, and also thorium, those heavy elements. So those are the energy sources, possibly. And finally, we can look at possible liquid media that we can use. So liquid is still very important for life, just because it not only transports chemicals, but it also dissolve molecules, and more importantly, actually engage in chemical reactions. For example, here it actually shows the reaction of a photosynthesis, right? So carbon dioxide is combined with water to form essentially sugar in the presence of light and enzymes. But is water unique? Can we actually replace it with some other kind of liquid media? Do we have other options? Well, the answer is yes, we do. And here is actually a list of some possible liquid media that we also see here on Earth. So we have ammonia, methane, ethane, and methanol. However, what we want to look for is actually for this liquid media to have a relatively large temperature range, which means it will stay liquid in most of the cases, right? So for water, the range is 100 degrees Celsius, which is, I think, 180 degrees in Fahrenheit. And if we're looking at this range, then 2 liquid media actually stand out. One is methanol, the other is ethane, right? However, ethane is not really possible, at least on Earth, just because most of the cases, it requires a really cold, freezing environment, and that doesn't work with Earth. So Earth's average temperature is around 15 degrees Celsius, and this is way below that. For methanol, it might be able to work, right? I mean, there's still like a 50 degree in Celsius range from the average temperature to its boiling temperature. But a common problem for all these alternatives is that they are not as common as water on Earth. So they might be possible on other planets or moons if they're more abundant, but on Earth, it's not likely. And water is also special in other ways. Aside from having a very high boiling point, which makes it very hard to turn to the gaseous state, right? So it's just a stays liquid as much as possible. When it turns to solid state, it becomes ice, and ice is lighter than liquid water, which means it will flow to the top. And in extremely freezing environments, that would actually prevent from all this water underneath from further freezing. And that would enable a relatively habitable environment for marine life to develop. If we have any kind of other liquid media, like ammonia or ethane, any of the solid forms of these alternatives, they the solid state would be denser and it would actually sink to the bottom, making this entire ocean eventually to freeze all over. And finally, water is a polar molecule, which simply means that its structure is not symmetric. So it actually has a charge separation, which means it has an end that is relatively negatively charged, and also possibly charged end is on the other side. Being a polar molecule, it makes water to be able to dissolve other polar molecules. For example, sodium chloride, that is a very important electrolyte for living organisms on Earth. It is also not going to dissolve membranes, which are made by non-polar molecules. All the other possible alternatives that we just looked at, they are all non-polar, which means they would be good at dissolving membranes, which is a nightmare for any living organisms made by cells. So all those were some of the conditions or substance life might need in terms of, well, given how they behave on Earth. And now we can also look at some of the properties that a habitable planet has. So one factor that is pretty important is actually the size or the mass of the planet. Because the bigger the size is, the more internal heat that it would retain. And that is important for actually keeping part of its mantle to stay liquid. So for our Earth, I mean, mantle might not look very liquid to us, but on a geological timescale, it actually moves just as a fluid. So when mantle behaves like fluids, they are actually convections that would drive the plates, and we call that plate tectonics, right? It would also lead to volcanism. So through outgassing, carbon that is trapped inside of the planet or the moon would get released into the atmosphere as carbon dioxide. And through rainfall, it dissolves in water, and it could also react with surface rocks and making them carbonated rocks. So all those rocks will later, through plate tectonics, to be recycled back to the mantle, completing this whole carbon 2 cycle. So this cycle is extremely important for us and large animals, since it regulates the climate and making the entire environment relatively stable for us to live in. And if we're considering a relatively small object, it will cool extremely fast. without being able to retain this internal heat. And that would make it lose the ability for any kind of ongoing volcanism or plate tectonics that would completely shut down the carbon-2 cycle. Sorry, the carbon dioxide cycle. Another factor that is relatively important is atmosphere. And I sort of already assumed that atmosphere was there when explaining the carbon-2 cycle. Atmosphere is typically produced by outgassing. And that typically means during the formation of the planet or the moon, there must have already had gases trapped inside of its interior. And through these geological activities, the gas gets released into the atmosphere, well, actually forming the atmosphere. And a larger planet will also help it to retain this atmosphere just because of the larger gravity. And finally, with an atmosphere, the water molecules are getting shielded and will not be that easily broken up by UV radiation from the star. And also having a decent atmospheric pressure will also help water stay liquid. And the reason that it's very hard for us to find liquid water on Mars is just because it's like extremely tenuous atmospheric pressure that would, any solid water that was present on the surface would immediately evaporate. And a final factor is the magnetic field. So a magnetic field actually helps retain the atmosphere by sort of shielding the entire object from the solar wind. And that is very high energy particles from space, typically driven by the host star. For our Earth, we have a magnetic sphere that just deflects all these highly charged, fast moving particles. And what actually would lead to a global and intrinsic magnetic field is some liquid metal inside of the planet, and also having a moderately fast rotation speed. So for our Earth, the outer core is actually liquid, and it's liquid metal. So as the Earth rotates, there are actually a tiny little bit of electric current that would induce a magnetic field. And that is actually how our Earth's magnetic field was formed. So that is very handy. And we're just hoping that some of the other possibly habitable planets would also have a similar environment. But again, these are all assumptions made only based on Earth. They're not necessarily what life needs to develop. A planet that checks off all the boxes may still not have life, or life can exist in, an environment that's completely opposite from this. So we're making our best guesses, but we still don't know. And next, we're actually going to take a quick look at some of the places in the solar system where it's considered as potentially habitable. First come to mind is Mars. Human actually started exploring Mars at a very early time back in the 60s, and there have been many missions focusing on possible Martian life. So two missions that I want to bring to your attention is Curiosity and Perseverance. Curiosity aimed to investigate Martian climate and geology, was looking for evidence for past water and also microbial life, and is conducting planetary habitability studies in the hope and preparation of human exploration. And Perseverance, which was formally named as Mars 2020, it landed on Mars in 2021. And it actually it's a sample return mission, meaning that it's collecting samples from Mars and will return those to the Earth for analyses. And it is currently seeking for seeking evidence for past life. Well, there are quite a few pretty solid, I consider it as pretty solid evidence for past water on Mars. And one example is actually around these landing sites for both Curiosity and Perseverance. They landed in the Gale and Jezero craters, respectively. And you could see that this is a landing site picture of the Jezero crater. And they are already sort of like channels or gullies carved out by flowing liquid on the surface. They are carefully chosen so that the rover can basically just travel around this kind of environment, collecting samples that are able, or that has a probably best chance to find evidence of past water. And another exciting evidence found by Curiosity was actually when it was traversing through the Gale Crater, it drove by an ancient stream bed where on Mars you could see these clumps of pebbles that just look like those on Earth. And we know on Earth, these typically form where there's water or lake, right, or rivers. More interestingly, chemical analyses of this region actually shows that the lake, the ancient lake that was at this location of the crater was perhaps once a lake with pure water that is drinkable. In other words, the Gale Crater, or at least a part of the environment on Earth, was almost certainly to be habitable in the distant past. And aside from finding water on the surface, studies on Martian atmosphere have also been carried out. Around last year, there was actually a very interesting discovery of Martian methane in the atmosphere. Well, on Earth, there's a significant amount of methane being produced by microbes that help livestock to digest plants. So that could be a sign of any Martian life, very basic Martian life to be present. But we can also not rule out the possibility that it's simply just a result of the geological activities. And actually, the confirmation of methane on Mars, there was also quite a story because both Curiosity and another probe launched by the European Space Agency, they were both there trying to study the Martian atmosphere, but one detected methane and the other one didn't. But both detectors were pretty reliable and also accurate. So they were like, then what is the problem? Is there actually methane in the atmosphere or not? So it turned out that they were not taking the measurements at the same time. So one took measurement during the day, the other was at night. And that was enough to actually cause the detection/non-detection of methane. And if we're also looking at, through a longer time scale, there's also a seasonal variation for methane, which again, it's so puzzling, which we cannot say for sure whether it's pointing to biological or geological origins. But it's a very interesting and it's exciting discovery. Well, so Mars, what we know about this planet is it was probably habitable in the past, given that we already saw solid evidence of flowing water on the surface in the past, not now, which would probably hint that it must have had a thicker and warmer atmosphere in the past. So Mars is about only half of the size of Earth. Well, I should say the diameter is about half of that of Earth. So it's not very good at retaining internal heat compared to the Earth. And it might have lost most of its atmospheric gas through, because of change in the magnetic field. And because of that, the surface pressure is way too low to make liquid water stable. And now Perseverance is currently on Mars, traveling through, drilling the land and collecting samples of rocks, Martian soil, and also atmospheric gas to later return to Earth. Another intriguing candidate is actually Venus, which is considered a twin planet of Earth by having very similar size and mass, and also composition. However, Venus has an atmospheric pressure that is about 200,000 times that of the Earth, and its average surface temperature is about almost 900 degrees in Fahrenheit, and that's comparable to a pizza oven. So I don't think any of us could survive that kind of temperature. So for a long time, it was actually not an interest in terms of research for many, just because its atmosphere is also containing a lot of, corrosive sulfuric acid. It doesn't seem life is likely on that planet. However, around last year, there was actually a study that discovered phosphine on Venus, well, actually in the atmosphere of Venus. So on Earth, bacteria produces phosphine, but again, we're not sure whether phosphine on Venus has a biological or simply just chemical origin. Currently, we think it's possible that there's life, but it's unlikely still, given how harsh the environment is on Venus. Aside from rocky planets, there are also moons of Jovian planets that we have been very interested in terms of searching for life. Out of those, Europa is one of, the one that receives the most attention. So Europa is the second Galilean moon of Jupiter. And just because it's very close to Jupiter, the gravitational interaction between the two is very strong. And Europa is receiving a lot of tidal heating, which simply means that there's a friction created either at the layer of, between the rocky surface and water, or there could also be strain created inside of a rocky planet or moon. So that seems to be enough to melt ice on the surface. So now we're thinking, okay, well, maybe there is a subsurface ocean on Europa. And there are actually some evidence supporting that hypothesis. So one evidence is that we see that the surface of Europa is quite smooth. It only has very few structures or features rising high up, maybe around a kilometer or so. There are very small numbers of craters on the surface, which is probably because that its surface have been already revamped by occasional breakthrough of the subsurface water or slushy ice. So those plumes are able to just completely repave the surface. And Europa is also discovered to be having an induced magnetic field, which pretty much suggests that there might be a salty ocean just right underneath the water that could conduct electricity. So to further study Europa and its habitability, NASA is sending an orbiter called the Europa Clipper to do close flybys of this moon. They'll collect images and also spectra of this moon. And there will also be radar data actually trying to see how thick this icy crust is on Europa. And it will also carry thermal instruments to study whether there are evidence for warm water just right underneath the surface of ice. And the Clipper will also look for evidence for water in the atmosphere. So this is a very exciting future mission that is just happening around the corner. That would definitely give us a lot more information about Europa's surface, atmosphere, and ocean. And there is another sort of comparable probe to be launched by the European Space Agency. It's called JUICE. It stands for the Jupiter Icy Moons Explorer. So there's a bunch of very, entertaining acronyms here and there in astronomy and planetary science, and this is one of them. So this probe will study 3 out of 4 Galilean moons of Jupiter. So it will definitely cover Europa. And so it's interesting that it will also be studying Callisto and Ganymede, where scientists already suspect that all of them might have subsurface oceans. So this study will actually reveal many more new information about the Jupiter moons. But aside from doing this exciting science, one significant challenge is actually for this probe to survive Jupiter's very strong magnetic field as it orbits around Jupiter and observe the moons. And another candidate is actually a moon of Saturn. It's Titan. In some ways, Titan is extremely similar to the Earth. For example, its surface pressure is only about 1.6 times that of Earth. It has a substantial atmosphere that's made of nitrogen, 90% of nitrogen, and almost no oxygen. It's able to retain this substantial atmosphere because of its relatively large size and also relatively cold temperature. We expect mostly water ice to be on the surface at a distance of Jupiter from the sun. And what's interesting is in terms of landscape, we see a lot of channels, rivers, or even lakes that are on the surface carved by liquid methane and ethane. And that is very interesting. Another very fascinating piece is there some evidence for icy volcanoes happening on Titan. So it might actually have some kind of like low temperature volcanism where the eruptions are driven by melting or vaporizing ices of either water or methane or ammonia instead of rocks. And if we actually make an analogy or comparison between the landscape of Titan and that of Earth, we can see that there's pretty good 1-to-1 projections. So there's liquid water on Earth, and on Titan is methane and ethane. On Earth, there's rock, there's magma and lava. On Titan, there's slushy ice and icy volcanoes. And also on Earth, there's dirt, and on Titan, there are some kind of smog particles. So here is actually an image showing some wind-blown dunes on Titan, which are just like some of the dunes that we see in desert on Earth. So we have definitely studied Titan in the past, and one pretty famous mission to both Saturn and Titan is the Cassini-Huygens spacecraft. So they were launched in 97. Huygens actually landed on the surface of Titan in 2005. Cassini was an orbiter to study Saturn, its rings and its moons, the whole system. So collectively, they gather a lot of data from Titan's surface and also atmosphere. So unfortunately, Cassini ran out of battery, just a few years ago, and it made a purposeful deep dive into Saturn in 2017, ending its legendary. Well, for Huygens, the probe is still there on the surface. It's just not working anymore. However, there are some exciting upcoming missions specifically dedicated to study Titan a little bit more. So this mission is called Dragonfly, expected to be launched in 2026. And it will actually make measurements of Titan's ground as well as the atmosphere. So Dragonfly is like a drone type of spacecraft. It will search for signs of life, both ancient and present. So in Titan's atmosphere, as we said, there's a significant fraction of nitrogen. There's also carbon, carbon, hydrogen, and ethane, and many of these elements that we could find on Earth. So Dragonfly will actually go there and pick up signs of how these chemical elements, if these chemical elements are making any reactions, and studying the environment on Titan in a lot more detail. So that is something that we can look forward to. So to sum this section up, what we can actually learn from Jovian moons is that life is not completely impossible in the outer region of the solar system. Even though there are no liquid water, we still have liquid ice, water ice, and also other alternatives that can survive in much lower temperature. Although it doesn't receive a lot of solar radiation, there are other types of radiation and energy source that it could take, including internal heat. And finally, if they were any kind of life forms in the outer solar system, we probably expect them to be pretty primitive, just because how cold it was, and the metabolism for these life forms would have to be pretty slow and different from what we have now. And finally, I wanted to introduce a little bit about life beyond the solar system. So there are also other star systems where planets just happen to be located in just right the area for liquid water to be able to survive on the surface. So for exoplanet studies, there have been Kepler missions, K2 missions, and also TESS missions, basically detecting all different exoplanets using various ways. And currently we have just over 5,000 confirmed exoplanets. And these are all planets orbiting other stars or other suns. Well, as you can see, some of those could actually be pretty different from our Earth or planets in the solar system. So depending on the initial mass of a star, it can go through very different evolutionary paths, right? And ending in different states. So one thing when we're considering, okay, what stars could be a good sun, is that whether, it will stay pretty stable for a long enough time that would enable life to develop, and what kind of death that this star would have and when. So one thing that we would consider is whether it would have enough heavy elements, including carbon, to enable any kind of carbon-based life. So for our sun, heavy elements, which really refers to anything except for hydrogen and helium, it's about 2% for our sun. However, studies have shown that perhaps 0.5% of heavy elements is already good enough to for life to be able to evolve and show up. And we also know that the smaller the stellar mass, the longer it actually takes to burn off all the energy or the fuel inside of the core. So it would actually have a longer lifetime for stars with less mass. And 90% of the stars in the Milky Way, 97% of the stars in the Milky Way actually qualifies for that. So I don't think that is a constraining factor here for us to find any life in the Milky Way. And finally, we also want this star to have a very steady energy output, which means it doesn't explode too fast, right? Or it's not giving out a lot of UVA radiation that is totally harmful for any living organisms on the surface of the planet. But at the same time, we also need to consider, habitable zones for all different types of stars. For example, we just said, okay, well, low mass stars, they're great for life because the stars can live for a long time. But at the same time, low mass stars, they also have narrower habitable zones, which basically reduces the possibility for planets to be found in this very narrow band around them. So that is a trade-off that we need to take into consideration. And in the exoplanet studies, we have actually found so many different exoplanets that it looks nothing like the planets in our solar system. So there's something called hot Jupiter, which basically means it's Jupiter mass planets, but orbiting the star very close by, and it has puffed up atmospheres. There's a super Earth, which is simply planets that are heavier than Earth. There are water worlds that are planets primarily made of water. They're sort of a hybrid type that's called terrestrial Jovian, which we don't have in the solar system. So it has a rocky and potentially metallic core, but it also has a substantial atmosphere, just as the Jovian planets. And finally, there are mini Neptunes, which are also called, I think, Xinnan planets. So those are hot planets that have a thick atmosphere and also a rocky core. So they're sort of like in the mass range of maybe like 2 to 3 up to 8 Earth masses. So there are actually all different kinds of exoplanets, enabling all different possibilities for extraterrestrial life to show up and evolve. Okay, so this is the final topic that I'm going to talk about is when we're looking at ourselves, we see ourselves as intelligent life, but is our selves being intelligent actually a chance event? Or otherwise, would there be any technologically advanced species to have been involved on Earth if there had been, a series of past events that prevented us humans from existing? I guess the answer is we don't know, because we only have one data point, that is ourselves. So searching for extraterrestrial intelligence or SETI, it has been an ongoing effort, and actually, where I'm located, and most of you, is pretty close to the SETI Institute, right? But SETI also is based on several assumptions, which means, okay, we're assuming that the intelligence is advanced enough to develop science and technology, that they are able and willing to send out detectable signals, and we are also able or actually advanced enough to detect those signals. So one way to do that, and people have been conceptualized this a lot, is to actually have send out a radio wave, radio signal that has a pretty wide band with a narrow band carrier. So the wide band would carry more information that allowed by this radio signal, and this narrow and very strong carrier would make the signal to be easier to be picked up. It's almost like, you know, in an ocean and you're trying to pick up, you know, a bottle or something. And we have done this in the past. And I will talk about the Arecibo just in a second. But another question we want to think about is, well, we have this broad band and narrow band carrier, but at what wavelengths? So one possibility is that we're actually sending this out at 1420 megahertz. It sounds very random, but that is actually the frequency emitted by hydrogen atoms. And if we look at a field of sky simply using optical or visible light, this is what we see, right? We see, you know, like 2 galaxies and maybe like 3 and a bunch of other stars. But if we're looking at the sky using this hydrogen emission, this is what we're seeing. So all these galaxies seemingly to be separated, but they are actually interacting with each other. These are all hydrogen gas that they're exchanging. So hydrogen actually allows us to see a lot more than what visible light cannot, but this is only one possibility, right? And we have actually sent out radio signals using the Arecibo telescope, which very unfortunately collapsed in the past year or so. So this is the message that we sent out. It was a 3-minute radio signal to a close by globular cluster so that we could reach, you know, as many stars or planetary systems as possible in a very short period of time. This is actually very interesting because to me, I cannot really recognize anything that we're trying to communicate other than this is a human figure, and that's probably it. I think this is supposed to show the Arecibo telescope. This is our solar system where we have, you know, the sun, and it used to be 9 planets. And these are the DNA helix, double helix that I couldn't really tell. So of course, there are a lot of information that we're trying to communicate, but if we cannot really even communicate among ourselves, and how are we expecting any alien life to be able to interpret that? So to sum it all up, we actually know very little about ourselves, about our environment, and also about others. We're getting there, though. So by studying life, we know better about ourselves. By studying planetary sciences, we know better about the Earth. And by studying astronomy, we know better about the universe. So whenever we're looking up at the starry night, there are just millions of possibilities that we're looking into. And there could be a civilization far, far away who may be very similar to us, and just wondering if they are the only intelligent life in this universe. So I'll leave it there, and thank you all for listening.
Great, thank you, Xinnan. Let's see, wow, I guess we got a fairly bigger audience here. Great. So at this stage, are there any questions from our audience? You can unmute and ask the question.
This is Ken Lum. What kinds of, the JWST is supposed to be, one of its mission objectives is to look for biosignatures in exoplanets. So what kind of biosignatures have people been thinking about of late?
That is a very good question. Well, I think, well, some of those include, you know, methane and also I think phosphine. So everything that is produced on Earth, or like produced by living organisms on Earth, is considered biosignature. But again, here is almost like my blind side as not being an expert in this field. But it is true that JWST will be, well, I guess JWST will be looking more into the atmosphere of exoplanets. And that is one of the key goals of this telescope. The other one is, of course, where my specialty is, that is the early universe, high redshift galaxies.
Okay, I have a question, I guess.
Mhm.
Given that your specialty is the early kind of life in the universe, I guess we're now, what, about 13 plus billion years past the Big Bang. It seems like certainly there's been time for many stars and planets to come and go. I guess, has there been any work done to say what's the earliest time life could have evolved into intelligent life? I mean, if we're looking like maybe 5 billion years ago, there was much more life than there might be now, or what?
Yes.
Speculate?
Yeah. I think again, the problem is we only have one data point, that is Earth,
Yeah.
right? That we currently have. So the earliest record of, or like a sort of hint for early time life, I think it dates back to around 3 billion years back. So it should be around that, maybe like 3 billion years or so. At least we are here today, and that seems to be long enough time for life to be able to develop into an intelligent life form. And I think 3 billion years was also around where, like the Martian climate changed a little bit. So that's why, I mean, it's still a question regarding, how long it takes for microbial lives or basic life forms to develop, and how long it takes for intelligent life to develop. So, for Earth and for our human beings, it's one data point, right? But I think maybe like 3-4 billion years, that's the ballpark.
Okay, and that would be 3 or 4 billion years since the start of since the Big Bang, or since the formation of the solar system?
Oh, okay. Yeah, sorry. I should clarify. It probably takes 3 billion years from the origin of life all the way to where we are now for developing intelligent life. In terms of after the Big Bang, I think as soon as the planetary systems, they get enough heavy elements, top 3 stars, which are among the first stars in the universe, they might be very difficult to form any lives, just because they wouldn't have enough carbon in there. But for stars that form around the solar system slightly earlier, and all afterwards, we should be good to go. So in terms of number, I don't have a solid number for you here. Yeah, in terms of like starting from when life could have been developed after the Big Bang.
Yeah, I guess if I remember some of my stellar formation, the first stars were primarily hydrogen. They had to go through a cycle to create the heavy metals, basically, and spread those out, and then reform new stars before you could get that 0.5% of metallicity in the your stellar systems to enable life to form. And I guess that would take, I'm not sure how long that takes, but I guess, yeah.
Yeah, and it would also differ a little bit from galaxy to galaxy, depending on what their star formation history would be like, right? Like how soon the next generation stars would reach that threshold, and whether that's 0.5% or not, that is the current, I should say, guesstimate. So it's very rough.
So I mean, in some sense, Marianne, is the production of microbial life on Earth came about quite quickly after the Earth was formed, in probably somewhere from 500 million to 1 billion years. But as Xinnan said, is it took about 10 billion years from the origin of the universe to create the solar system and the composition of the solar system that had enough of the heavy metals to make that possible on Earth. But I believe that the production of carbon could actually happen fairly quickly in the largest stars, which I don't know how fast they go through their stellar cycle, but my presumption is that they can probably do that within a couple 100 million years to produce sufficient carbon. And so in theory, if it took a couple 100 million years to make sufficient carbon, and then a solar system was made from that sufficient carbon, is the production of microbial life from that sufficient carbon happened within probably 1 billion years, if not less, perhaps 500 million years. But getting from microbial life to quote intelligent life arguably took about 4.5 billion years, because intelligent life on Earth has existed for arguably less than 20,000 years, depending on how you define intelligent life. But I sort of, my question that was sort of sitting here is if you define intelligent life as human-like intelligent life, are you discounting the intelligence of, shall we say, dolphins, who have a high level of intelligence, but they do not have opposable thumbs and so forth to create, quote, technology? And also for crows and so forth, who have a fairly high level of self-consciousness and so forth, but similarly don't have an opposable thumb to be able to create technology in the same way, although crows do make tools, fairly simple tools. Or moving even a little bit backwards is something like an octopus, whose brain is actually quite sophisticated and so forth, and it doesn't even have a backbone. So, what happens out of this thing is that the step to intelligence has a huge component of prejudice / as you say, is one example, in large part because we define it as one example. And our selection process for what we would look for and the ways we look for it are such that we would miss all of the dolphins and the crows and the octopuses out there in the universe, because they don't have sophisticated technology in the way that we define what sophisticated technology is.
Absolutely. I mean, that is a very good point, Ed. So yes, in terms of if we are doing doing study, right? Intelligent life such as dolphins, those would definitely be missed. And there's actually, so this is another kind of definition that we have no idea how to put. So what actually defines intelligence, right? Or like intelligent life? That is another big question. And how do we measure it? To me, it seems like it's a continuous spectrum instead of like, just like module, whether it's intelligent or not. So there is actually, I'm just gonna quickly share my screen again. So it's one of the extra slides that I prepared, where it would actually talk about, you know, one way, not the only way that we measure intelligence, which is, you know, using EQ, and that's basically defined by the ratio of their brain mass divided by their size, right? So humans are here. We have an EQ of 7, and I think the next one is actually dolphins. And elephants are also pretty smart. They could even draw. They could follow a lot of tasks. But as you said, you know, there are different, not only biological constraints, but also, you know, if they're able to develop beyond that, there might also be, you know, sociological reasons that they are not really advanced in science and technology to be able to, you know, sign up signals. Yes, so that is totally valid comment.
One point I may make about the encephalization quotient is, as I understand it, is brain mass. This is based to some extent on the presumption that the organization of the brain and the density of brains are a mammalian type organization. And I will say that in a way that has only been recognized fairly recently is that birds have smaller neurons. And as a result of that, they can get more processing done with a significantly lower mass. And the amazing thing out of this is it's almost the equivalent of microprocessors, okay, is that they have the capacity to do more processing with lower mass, in spite of the fact that they have more connections within their brains than humans. And once again, there's shall we say, prejudice that sits here because the underlying physiology of mammals is based on the evolution of mammals, and birds actually evolved in a stage long before mammals. And in some ways, as birds are exquisitely evolved to be very low weight, so they can fly.
Yes.
And as a result is they have the capability of being able to decrease the mass of most of their organs at various stages in their life, or dispensing with them in certain forms, so that they only use them at the point in their life cycle where they need it. But I actually had a second question, or a point that you made with respect to the liquid form of these molecules and the temperature range.
Yeah.
Is those are at 1 atmosphere. And I thought I'd ask you if you had actually looked at how those ranges change as the pressure changes, or if in other words, is if you modify the pressure, is do the ranges of liquid phase change significantly in a sense such that the phase transition things just have weird shapes and so forth?
Definitely, yes. That is a very, very great comment. Yeah, so again, you know, there are, I would say, so many different unknowns and different parameters that we're trying to figure out, right? So it's more like, okay, well, what if we just assume it's at 1 atmospheric pressure and then try to figure out the other things. But as you said, you know, I personally don't know whether they've done the experiment to figure out how the temperature range would change with atmospheric pressure. But I think that one is definitely very valuable to do. Well, we're not expecting, you know, all the other planets just to be like Earth. And a lot of these assumptions, I mean, I don't blame ourselves to make, you know, human-centric assumptions, simply just because, you know, we don't really know better. We haven't really seen another, like a different kind of life form, right? Like including assuming that a larger brain mass just simply means more complicated behaviors. That is still a big question mark there. I guess, yeah, there's just so many unknowns, and even based on, I guess we would have to have some kind of like foundation, right, to proceed with studies. And these assumptions, once we've figured something out, we could actually look more closer into these assumptions. But yeah, they're not, they may be way off.
Well, that's a fascinating talk and a remarkable subject, and one that has a lot of intrigue for, particularly for humans. I guess we just don't have enough of a baseline to be able to do more than wildly speculate about what could be or when we'll discover it. Are there any further questions? Okay, well, we know how to get in touch with you, Xinnan, in case some do come up. And we want to thank you very much for your lovely presentation. It's very intriguing and very interesting.
Well, thank you very much for having me. And I hope I didn't raise more questions than I answered. I figured I probably didn't answer any questions, any of the big questions.
No, but you certainly stimulated all of us to think. And that gives rise to further questions and also to further understanding.